All right, so welcome to another application of using a definite integral. Okay, so here in this problem we are going to explore how definite integral can be applied into solving a physics problem right here. And so definitely viewers for this the kind of application are on track for heading out to a physics field, or at least taking some courses in physics. Okay, so specifically here we would like to find out how we can apply a definite integral into calculating work done on an object like that. Okay, so we definitely have to borrow a few ideas from physics, even though this is a math course, yes, but we do need to borrow and bring over a few ideas from basic physics course right here. Okay, so anyone here have to understand that anytime we perform an action, there's force to perform that. See, if I just swing my arm out, there's force for me doing that. Okay, I'm lifting an object, say for example my calculator on my desk right here, now lifting it up. Okay, I have to exert some force in formal physical term right here. So lifting up an object, I have to exert some force. Okay, and then or pushing my mouse right here around on the desk right here, it's an object, so I have to exert some force. So we're not talking about how large or how small the force is, but any time that you're doing any time that you would like to cause a motion, okay, any time you are about to cause a motion, you got to exert some force. And so just like that, like I was demonstrating earlier, I was lifting up an object, okay, so I was exerting some force to pull it up or push it down, okay, because so in a way how we've been understanding according to Isaac Newton, so a force is simply a push or a pull. Okay, either we're pushing it, we pull. So lifting it up is also a way that we're pulling it against the gravitational force that's pulling it down like that. So we're pulling it up to go against the gravitational force that actually pushing it down. Okay, and so so now what exactly is work? Because all of a sudden I was introducing about work, and then all of a sudden I headed completely into force. Now work and force are directly related, are always related. So as I was demonstrating earlier, with this object right here, my calculator in front of me is an object, right? It has a weight, it has a mass right here. And now as I'm lifting it up, so I'm exerting force. But now what matters now is that how much distance I exert. So I exert that force to move this thing in a distance. So now it comes to the concept of work and energy right here. So work is so energy is converted into force, so that I can use force here to push or pull an object in a distance. Okay, so now so work is defined as how much force we exert, okay, to push or pull an object or lift an object to a certain distance. Okay, all right. So that's the one basic fundamental from physics that we have to carry over into this math course right here. So force is a quantity. So now work, notated by a W, a capital W, okay? And so work is the amount of force, traditionally notated by a capital letter F right here. But we multiply force with a distance, okay? So, and lifting up is not the only way. A lot of time, when we're doing our daily, household work right there, we have to, or imagine that you are pushing a heavy object across the floor. So there's a distance that you are pushing it, okay? And so as you are pushing it, you're exerting force on that object. And then you have to constantly exert the amount of object. You have to constantly exert the same amount of force to push that object in a certain distance, okay? And at this problem right here, in this work right here we're doing, let's not be too worried about the direction of where the force is. And when you actually take this understanding and go into your formal physics class right there, where you're going to even be more exposed about how you're dragging your object in different direction, that will come after. But this part right here is a fundamental. It's always the amount of force multiplied with distance, total distance that you're pushing that object to travel right there. Then that is going to be the total amount of work. Okay, so the idea now is always about we have a path that has a distance. We have a path, and then there's an object that we're trying to make that object. We're exerting force to move that object from a point on the path to a different point on that same path like that. And so moving that it's changing this, moving that object along a path is creating distance. But then as we are having force exerting all along the way over here, then that's how we spend energy of doing that. And that's why there's work with that. We can measure how much energy, how much amount of work that we have done in order to move that object from a position to a different position where there was a distance coming along. Okay, and so that's the fundamental. That's the basic idea about work right here. Work is famously force times distance. And so now where's the calculus? What's the part that calculus can come in right here? So now let me bring up a scenario right here. When we're starting out learning at a very basic level in physics right here, then usually force and distance are assumed to be at a constant level. So for example, if a man is say we're on the floor right here and there's a heavy object right here, and then this man is trying to push it. Okay, so we have this man right here. We have a man, okay, and trying to push this object. Okay, so this man is trying, see how he's trying to lean toward right there and trying to push that object. And so the man is trying to push that heavy crate across the floor, and let's assume that it just goes constant distance. So if he's pushing that heavy object using 500 Newton. And by the way, so in case anyone haven't been aware, then anyone hasn't been aware, so force is on standard as an international unit. It's measured in terms of Newton. Okay, and so 500 Newtons, assuming that he's pushing that at a constant force across that path, and let's say he needs to move that in 1 meter. Okay, so from here to here, he's pushing that in a total distance of 1 meter. All right, and so now that means in that way, then the total work amount that he has done, so work is another term, is another form of energy. How much energy he spent into pushing that object like that. Okay, and so the amount of work, the amount of energy he spent doing that is going to be calculated in quantity as 500 newtons, but pushing that all along 1 meter. And so right now I'm starting up with this scratch example, with this very basic example using completely standard basic units. So newtons and meters right here. And so now 500 newtons times 1 meter. So now the amount of work there is 500 joules. Okay, 500 joules. All right. So now with this 500 joules right here, that's, we call it, it's the work for him to push that object right here in a distance of 1 meter. And so once again, that's the fundamental. Okay, and so what I'm trying to point out at this point right now is that from the very first day we get introduced to force and work and all that. Then usually in the problem we've been doing there, in those problems we were doing there, then force and distance are assumed, are started at the starting level to be constant amount. Okay, like somehow if the man can maintain a constant amount of force, 500 newtons all along that path there, then work is simple. Calculating work is simple. Just one simple calculation, one simple multiplication problem. 500 times the distance here, and that's 500 joules. Okay, but then as we grow, so that's situation, the idea stays the same. But now as we grow more mature, we can realize that it's actually not easy at all to maintain the same amount of force all over. Okay, just think about the situation where, there's a situation where, the floor, even on the floor, he's pushing. At some point, the floor is smooth, so he has to exert less force. And then at some other later part of the floor here, the ground become more rough, more frictions. That's holding the crate back. That's why the man, he has to exert more force. So what I'm trying to say now is that now we are in the calculus class right here. Now we're at our level. We're learning about calculus class. We can no longer assume that force here is constant throughout the whole time. Force could be changing. So the situation here is force could be changing throughout the whole time. It could be less force here, but as the man pushing that forward right here, then he has to keep exerting more force to the point that he can't even realize how much force he's doing instantaneously anymore. Okay, so that's the idea. So we got force being non-constant. That's one situation. Okay, and then there could be other situation where maybe he's maintained a constant force, but who knows, his distance keep changing. I mean, he's changing. I mean, he's pushing, and then all of a sudden somebody else asks him to push it further. And so all of a sudden somebody else is to ask him to keep pushing it further, meaning the distance keeps changing and getting more and more and more. So cumulatively, how much work is he done? I mean, how much work has he done when he's really all finished? And that's the idea right there. Okay, so now I start using that term cumulatively. Now allow me to erase this picture here a little bit. So all I need you to understand now at this point is that force and distance can change. Force and distance at our level here is no longer, either force and distance here is no longer a constant quantity. We have to allow either force or distance, or even both, to change as a variable. Okay? And so in that way, now I come up with the concept here. So really, in the end, total from beginning to the end right here, from where he start pushing the crate, from where the man start pushing the object right here. See, again, I'm going to redraw the picture of that man. Okay, with the two hands, he's pushing it. So the man here is pushing that, but in the end, from the beginning of when he starts to when he ends, it's not just strictly about beginning of the path and ending up and to the end of the path, but since he beginning to push, since he beginning pushing to when he's finishing his pushing work right there. Okay, we come up with what's so-called a total work, total W. All right, so total W here has to be, and in what I described earlier, it could be that as he's pushing, the floor was smooth as fast, so less force. And then as he's progressing toward the end of his path, like there, of that distance right here, then the floor at some point become more rough, or the floor was smooth and then rough and then smooth and then rough, meaning he has to exert different amount of force. Okay, and so that's why in the end it's best to accumulate the amount of work in each little section. Maybe in the section where it's smooth, okay, and then rough. In this section here, it's rough, that means more force, okay, and then it's smooth again, but maybe not as smooth as the other case right here, okay, so smooth, rough, meaning more force, and then getting back to smooth, but probably not as smooth as how he started out, or even more smooth, okay, so some amount of force, much more force, okay, in a certain distance, some amount of force in a certain distance, much more force, and then so much little force. Just so little amount of force. I shouldn't say so much little force, sorry about that, but it's just so some amount of force. So much force needed here, just for that long, lengthy distance, and then he all of a sudden everything's like flying, just little amount of force. Even when you're driving, it makes your car has to work differently, depending on whether the road surface is smooth, okay, and then when you go into some rough road right there where it's all just, crazy, the gravels and all that, okay, it's different amount of work that your car is going through like that. All right, and so, but the idea to get the total work from the beginning of the path to the end of the path, we have to start accumulating. We have to start accumulating the amount of work in each little section right here. That's one case I can bring up right now. So the main idea now, the main fundamental I would like to point out now is that anytime we would like to do a total work, to calculate a total work, and now with our understanding in calculus right here, total work, can be done by accumulating. An integral is accumulation. So how about, you see each little amount of work right here, allow me to call that little amount. Little amounts of work. Okay? So total work come out from accumulating. So this sign right here is the integral sign, ladies and gentlemen. So I want anytime you see this symbol, outside of reading that out loud as it's an integral sign, it's accumulation. Okay, what are we accumulating here? What are we accumulating here to get total amount of work? We're accumulating all of the little amounts of work. Okay, so that we can reach to the total amount of work right here. Accumulation of all the little amounts of work. And then we're accumulating that from a start, from where we start our pushing work to where we end our pushing work. Okay, so that's how I want any of my students or anyone studying with me to see that fundamental before we apply definite integral into calculating total amount of work. Okay, so calculating total amount of work, we first have to understand an integral is accumulation. And so here in this case, what are we accumulating? We're accumulating all the little amount of works. Okay, all the little amounts of work. And then as we successfully accumulating all of the amounts of work from our start of the work to the end of the work, right there. That's where we got the total amount of energy, the total amount of work right here. Okay, and so in that way, allow me to also introduce. So many textbooks, many textbooks refer to that little amount of work. It takes a lot of deep understanding to get this, but at this point right now, allow me to briefly explain as following. Many textbooks use the following symbol. See, work, but little amount of work is a DW. That's for little amount of work. We're accumulating all the little amount of works from a start, okay, to the end. That's to get us total work, total W. Okay, so this is the fundamental that I want anyone studying with me and who is about to apply calculus into finding work right there. Take that fundamental with you right there. Okay, take that fundamental with you, and then anywhere we apply. And then so of course after I generally discuss about the situation, I am going to start exposing you to different various situations where you keep seeing this fundamental comes out, and that's how we're going to be successful. Okay, in terms of finding work. Okay, all right. So now allow me to demonstrate in another. Bring up a few scenarios here, and these are not our examples yet. Okay, these are not our examples yet. But see, just about the man right here, there are a couple just talking about accumulating all the little work, Sometimes there's students who study with me got hung up with that little concept of mine when I explain that. What does it mean by accumulating a little amount of work? Okay, so let me point out a couple scenarios. I already brought up that situation, that case about the man pushing. There's a man, okay, pushing that heavy object. Okay, he's pushing it. The man is pushing it. This object is heavy. Okay, and so here's the thing. Think about, there's a mean person, a person not so nice. Okay, so when the man at first starting out to push this thing, then the object here is at whatever mass that is. Okay, and then as the man here is pushing the object along the floor, there's a mean person magically or hiddenly keep dropping more, because this object here could be a container that has heavy stuff in it. And so initially it started out with being maybe 1,000 kilograms or something like that. 1,000 kilograms. I mean, it's probably a little too much. It's a little over exaggerated for a standard sized man to be able to push 1,000 kilograms. But well, let's say whatever mass that is. Okay. But now initially the man starting to push, and then initially he planned to push at a constant amount of force, exerting on that mass. And then there's a hidden person, there's a mean hidden person as he goes along, as this man is going along, there's another person secretly dropping more objects into that crate, making it heavier and heavier and heavier as we go along, as the man goes along. So as this man keeps going along and without realizing that somebody is constantly leaving more objects into his box right there, then what do you think he will feel? This man will feel. He's going to feel that he has to exert more force. He has to keep increasing his amount of force in order to be able to maintain the pushing. So in that way, here's how I see it. Little amount of force means, little amount of work here means, hey, just maybe in some small instance, in some small change in distance, some little change in distance, okay? In some small change in distance. Then you see, because it even takes time between for that secret person to keep dropping more object in there. So between each time that there's a new mass being added in right here, between each time frame, then that distance there, the distance where the mass can stay the same for a little while, then with that little distance, okay, I can call that it's a little distance. You can multiply that, or how about it's a distance 1, a d1 distance 1. We multiply with the amount of force that he's doing there. So for that small little distance, okay, just a little distance. And then that's how much force, but see, it's a little, so that's how much force, but only existing in that small amount of distance. And then when the crate, when this object right here, this container is being pushed to that, to finish that little distance, then it gets heavier because there's that secret mean man keep dropping more objects into him, into that box, making it heavier. And so after that point right here, the mass got heavier, so it becomes, this man has to exert a bigger force, a larger force to go another distance, d2. See, to go another distance, d2. So from here to here, that's a d2. This is a d1. Okay? So from here to here is a d2, and of course, like I said again, we already had a change in force amount to a different force amount right here. So we got to be accumulating. Okay? And then now there's another small section of, okay? And then past that point, once he finished with that d2 distance, then this secret man here and so mean man right there drops another object. Drop another heavy object, adding more mass into this container. And so that means on the third distance, d3 right here, just as short, no matter, it's not the point about how short or how long, but in a some distance, d3, then the mass here already changed to a different mass, so meaning this man here has to push that object in this distance, in this small distance, another third amount of force right there. So F1, F2, and F3 are all different amount, okay? And so by the time that he reached to here, then maybe, oh my God, this man is too tired because he got to push so much, and it's not even a constant amount of force. He has to keep pushing it and keep exerting more force on the little different distances like that. And so, ladies and gentlemen, each one of these is what I refer to, and honestly, I'm not sure how often this mean man will keep dropping more heavy object into that container. So the point is, we just don't need to worry about how many more times this mean man is going to keep adding more mass into that container. Okay? Only from that starting point to this ending point, he can, if he's fast enough, he can instantly keep adding more. So the amount of distance here is going to even get smaller and smaller. But so in the end, fundamentally, each one of these is what I refer to as little work right here. Okay? Little work amounts. All right? Little work amounts. See, these are all the little work amounts right there. And we can expect a lot more. And that's, see, adding up, that's what I'm doing right here, accumulating. I'm accumulating all the little amount of force. That's why, once again, right here in this scenario, that's accumulation of all the little, okay, work amounts. That's precisely what it is, okay, from start to end, just to get total amount of work. total amount of work from counting from where he began pushing to where he finished pushing. Okay, and just like that, standard textbooks use the formula, the convention notation right here, dW. At some point, I will have a formal short talk to sort out all of these D things right here that you have seen scatteredly throughout different applications already by far. Okay, assuming that you're watching this after already viewing some other applications, and then from a start to an end. Okay. This is only one situation that I'm trying to convince viewers, or I'm trying to convince anyone studying it with me about getting a total work. It's all about accumulating the little work amount. Okay, in that situation. All right, so let me bring up another scenario to convince you again that it's all about to get the total work. It's all about we are accumulating little amount of work. So how about this time? The same man pushing all right. This man is ordered to push a container that has heavy rocks in it. Okay, so these are all the heavy rocks in it. Okay. This container has all that heavy rocks in it. And we don't even have to assume that all the little pieces of rocks here have the same mass. We don't have to worry about that. So here's the thing. This man is ordered to push that amount of that container. So at this point, it's being the sum of all these mass here, right? It's a total mass. This man is ordered to push that total mass from a starting point to an ending point on a path right here. Okay? And then of course, because this object here, this container here has a total amount of mass that come up with all these rocks right here. And so he has to exert a force. He has to exert a force. Oh boy, if it's a lot of rocks, he has to exert a lot of force, right? A huge amount of force to push that one box, to that distance. So ideally, that's how he's doing. Force, if he can somehow think about, there were times that, any one of us, maybe there were times that we have to push a box that have all the heavy boulders in it. Okay, the heavy big rocks in it. Heavy ones. Okay? So think about how much force we have to really exert to push that container, to push that box. 1 meter, 2 meters, 3 meters, 10 meters. Okay? If we're strong enough to exert one constant amount of force going all that path right there, then yes, total work is simple calculation. Total W. That amount of force constantly multiplied with that distance. But maybe the situation is not as ideal as we want, okay? The situation is, how about it's too heavy? The mass is too much to the point that is way above, way beyond our human capability. So the man becomes smarter. Here's how he's doing it. He comes up with a plan. Okay, he comes up with a plan. So what about, he's going to pick out an object. Okay, so I'm going to now delete one object here. All right. That object has a mass, much little mass. That means he's going to only need to use little amount of force. Smart man. Pick out a small object. That's a lot of time, that's what kids do. Right? We picked out a small object instead of the child tried to push a whole thing maybe too heavy for him or for her. The child is going to pick out a small object, move it fast. Okay? So less force on a smaller object, get moved. So maybe distance is the same distance from the end. So same distance, but now a less amount of force. Let's call that F1 times that distance. And then he comes back here. Okay, comes back here. Pick out another one. So now I'm going to erase another one. Okay. This one here, I'm not saying it's this second rock, I'm not saying it has the same amount of rock, it's the same mass. But it's some mass, definitely less than the whole container here of all rocks together. And so that second one, the man is going to pick out that one. from that same starting point, moving it to the end right here, it's going to be an F2 with that same distance. Okay, that's another little amount of force, but two different little amount of force. It could also be the same, but I'm talking now about this is a one little amount of work. This is another little amount of work. Okay, and then here it's F3 right here. It's the same distance. He's going to pick another one. Okay, he's going to pick another one and moving it. Okay, and pick another one and moving it. Now less rocks remain, and then it's going to be an F3. So that depends on how many rocks he has, the total work, one piece of work, another piece of work, another piece of work, all of those until he finished. This is total work again. Okay, it's total work. That's what it is. Adding up all of these. Adding up all of these. All right. And so in that case, the action that we're doing here, adding up all of these little amount of works, little work amounts right here. It's another way of saying what that smart man is doing. He's accumulating from a start to an end, right, of all of his little work amounts. That's another scenario that way we can see right there. Okay, and that gets him total work, or another way of saying he's accumulating all of the little work amounts. Standard textbooks refer to that as a DW. Okay, that's the same way. That's how I would like to emphasize about that concept there. Now when we are about to apply calculus into finding work, where force and distance can become a changing variable all over here, then that is the concept that we always want to stay focused to. Doesn't matter what situation we're in, but as long as you're calculating work, you want to always think about we're accumulating little amount of work or little work amounts. All right, that's the only fundamental. And so now I'm about to start walking you into different examples. Like there are different. I see every example here is an independent example, so I'm not necessarily going to order these examples into example 1, example 2, and so on and so on. I'm changing style a little bit in this particular lecture, even though you may see it throughout many of my other lectures. And some lecture I'm going with example 1, example 2, because those are related to each other and they rise in the level of difficulties. Okay, but here each example is on its own, and it has its own special and it has its own specialty where we have to apply things on different levels of creativity right there. Okay, so in that reason, I might not at all indicate that, hey, this is example 1 or hey, this is example 2. Okay, but I will just simply design them as separate, discrete, independent examples right there. But any one that you're seeing, any one example I'm pointing out later on in the video lesson here, in the video lecture here, will be focused. We'll stay very focused to this only fundamental. To calculate total work, it's an accumulation of all the little work amounts from the start to the end. All right.